right, so chapter 5 is about roots and rational numbers, and let's see. I'm just going to see how many lessons there are in this chapter. All right, so 37. All right, so in order to get through this whole chapter, that would be 7 lessons plus the test. That would be 8 lessons. So we're shooting for 5 lessons a week. Since you didn't get too much done last week, if you want to do more, maybe you could finish this chapter, but that's a lot because this chapter might be a little bit confusing. So roots are inverses of a power. So what does that mean? If we have x squared, okay, that means we're taking x times x, okay? Or if we have 4 squared, that means 16. Square root of 16 means we're trying to figure out what times itself equals 16. So instead of saying a number times itself and knowing what that is, now we're trying to work backwards. We're saying we'll start with this, and now we're saying what can I do? What can I multiply by itself to get that? Another way to think of that is if I have a square and the area is 16, what does the side have to be in order to give me the area of 16? And this is where we get square root. What's the square root of 16? What number times itself is 16? And this is 4. This is called the radical sign. This is called the index. And if there's nothing in there, we assume it's a 2. So if we just see this, that means we're trying to find the square root or the second root of something. What times itself will equal that? For this one, this is the cubed root. So in the index here, we have a 3. So we're looking for something times itself. X times x would give us 8. What number times itself 3 times gives us 8, and that's 2. The fourth root of 81, what times itself 4 times would give you 81, okay? And as these get more complicated, I find it helpful to do factor trees. So we could say like 9 times 9, 3, 3. All right, so we still have 81 in here, but now we just have it listed as its string of prime factors. And look at, we're looking for things that we have 4 of. 1, 2, 3, 4. So 3 times itself 4 times is 81. So the fourth root of 81 is 3. And if we wanted to do that with like square root of 16, we could say, well, 4 times 4, 2, 2. So square root of 16 is the same as 2 times 2. And we're looking for things that there are 2 of. There's 2 2's here, so I could take out one pair of those. The square root of 2 times 2 is 2, and the square root of 2 times 2 is 2, so that's 4. So kind of a trick that will always work is if you're trying to find the root of something, you can write it out as a string of prime factors, and then whatever's in the index here, you look for pairs or things, that number of sets. And if you have that, you can pull it out. That would be the root of it, and you multiply them on the outside. All right, and here we can see, you can see how these are related. 2 to the third power is 8, or if we say 8, what times itself 3 times equals 8, or the third root of 8 is 2. So you can see that it's kind of like addition and subtraction undo each other, multiplication and division undo each other, roots and powers undo each other. All right, next one. Okay, the Pythagorean theorem. Remember, Pythagorean theorem is a squared plus b squared equals c squared, and c is where c is like the hypotenuse, so the one that's across from the right angle. Or we could say leg 1 squared plus leg 2 squared equals the hypotenuse squared. We can see it written either way like that. So here, because we have a right triangle, we could call this A, B, and C. Well, we'd say a squared plus b squared equals c squared. Or 16 plus 9 is c squared, or 25 is c squared. All right, so now here, we have to undo the power. So if we were multiplying, we would divide. If we were adding, we would subtract. So here we're raising it to a power, so we have to take a root. Because we're raising it to the second power, we're going to take the second root, and that undoes that. So we get c, we get square root of 25 equals c, or 5 equals c. What times itself is 25? It's 5. All right. And kind of a cool thing, we could think of this over here. If we squared this, we could say that the area for this would be 9, okay? And then the area for this, if we squared this side, would be 16. If we add 9 and 16, that's 25. So this one over here, if we made a giant square over here, the area for this one would have to be 25. And what does the side lengths have to be? If it's going to be 25, it would have to be 5. So that's just kind of a neat visual. It's like we're taking the square of both of those legs and combining them, and we'll get a bigger square that's equal to the hypotenuse. All right, so for this, 1 squared plus 1 squared equals c squared. So 1 squared plus 1 squared is going to be, so this is 1 plus 1 equals c squared, or 2 equals c squared. Now to undo that square, we have to take the square root of both sides. So that gets rid of that. So we have c equals the square root of 2. And that is going to be an irrational number. That's going to be a number that has a decimal that goes on and on forever. 2 is not a perfect square. So if we had a square with an area of 2, there's no whole number that's going to let us have those sides. Okay, so irrational numbers are numbers that can't be written as whole numbers, fractions, or decimals. If you wrote them as a decimal, they're never going to repeat. They would like go on into infinity forever without repeating. So some numbers you can write as a fraction or a decimal plate that ends or repeats, and some numbers will go on forever. Square root of 2, square root of 3, or the cube root of 5 are irrational numbers. That means that if we put it into a calculator and wrote it out as a decimal, it would go on forever without repeating. How do we estimate irrational numbers? So square root of 2, square root of 2, well, 2, if we think of squared numbers, we have 1 squared and 2 squared. 1 squared is 1, 2 squared is 4. So 2 is going to be, we have 2 and 3. So 1 times 1 is 1, 2 times 2 is 4. So we know that the square root of 2 has to be 1 point something because it's between 1 and 2. And it's probably closer to like the lower half of 1 because it's closer, 2 is closer to 1 than it is to 4. So we can just kind of get an estimate, like maybe, I don't know, I would say like 1.3 might be a good estimate. And we could kind of like play with that and see what we get. 3 times 3 is 9, 3, 0, 3, 1.69. We could see 1.4 and see what we get. So that would be, that one's really close. So it's probably 1.4 something. So 1.4 is an estimate. So if we want to try to figure out, if we're trying to estimate the square root of a number, we can think of the perfect square that comes before of it and the perfect square that comes after it, and we'll get an idea about where the number might be. All right, multiplying and dividing irrationals. So these rules are very much like the exponent rules from the last chapter. Square root of 2 times square root of 5. These both have the same thing in the index. So because the radicals match, we could just combine them. That's the same as the square root of 2 times the square root of 5, or square root of 10. And how do we know that this is right? Well, if we look at a number that we have that perfect squares for, square root of 4 is 2, square root of 9 is 3, and that would be 6. Square root of 36 is 6. So it works when we have perfect squares, so we can kind of test and see that it works. It also works with this. So because the index matches on these, we're able to combine them. So third root of 4 times third root of 5, that's the same as third root of 4 times 5, or third root of 20. And if we wanted, we could do the prime factorization to see if we can clean that up. 5 times 4, 5, 2. All right, and there's nothing that there's 3 of in there, so we can't simplify that at all. There's nothing we can pull out. So the rule looks like this. If your index matches, you are able to just combine them under the radical sign. Same idea when you're dividing. So if the index matches, you can just combine them and divide. So square root of 21 over square root of 7, you could just say square root of 21 divided by 7 or square root of 3. Square root of 16 divided by square root of 4, same as dividing it. 16 divided by 4 is 4, and that ends up being 2. All right, same thing with this. All right, so for this one, we can't combine these because they don't match. They're not like terms. And we could see, we're looking for square roots. So we could see if we could clean this up and get the indexes, the numbers on the inside to match. 3 times 2. All right. And yeah, so we can't clean that up at all. So we can't put those together. So square root of 2 plus square root of 6, it just has to stay like that. And you can see that we can't just combine them if we look at numbers that are perfect squares. So if you're ever stuck, just put perfect squares in and see if it works. So this would be 3, this would be 2, so that would be 5. And if we say 9 plus 4 and we combine them, that's square root of 13. And the square root of 13 is not 5. So those don't work. Same thing with subtracting. If the numbers if these numbers don't match, we can't combine them. But if we look at this one, we have square root of 5 plus square root of 5. These match, so we could treat them like terms. We could say I have 2 square roots of 5. Because these match, I can treat them like terms. So I have 10 square root of 2. Same with subtraction. Because what is inside the radical matches, we can just subtract them, treat them like terms. All right, so this is what I was telling you about. You can do the prime factorization, and then you can cross out anything that's the same. So square root of 12 here. Well, let's see. This is 4 times 3, 2, 3. So square root of 12 is the same as the square root of 2 times 3. We still have 12 in there. And because we're doing square root, we're looking for things that we have 2 of. What's the square root of 2 times 2? It's just 2. So it's going to be 2 square root of 3. So do the prime factorization, and then you can pull out whatever's in the index there. If you have anything that has a set of that many numbers, you can pull out one of them and put it on the outside. All right, so if it's a third power, let's see, if we're trying to find the third power of the square root of 12, well, we just said, I'll do it again, 2 times 3. I'm sorry, they're doing it for 24. Third root of 24. Well, let's do 6 times 4, 3 times 2, and then 2 times 2. So what do we have 3 of these? So we can take out a 2. So it ends up being 2 third root of 3. All right, here, looks like we can't combine those, but let's just try to simplify square root of 18. That would be 9 times 2, 3, and 2. And we are doing square root. And look at, we can pull these 3's out. So we have 3 square root of 2 plus 5 square root of 2. So because we could simplify that, and now our radicals match, we can combine them. That's 8 square root of 2. So when you're working through these, do the prime factorization, see if you can get the radicals to match. And if you can, you might be able to simplify them further. All right, so when you are multiplying, like you have to distribute these, you could probably kind of see here, just like we can't combine these in here because they don't match in there, and we can't simplify them to get them to match. But we can combine 2 times 3 is 6. So we have square root of 6 plus square root of 14. All right, and now let's see if we can, this is 7 times 2, and this is 3 times 2. But we're not able to cancel anything out, so we can't get those to match. So the furthest we can simplify this to is just square root of 6 plus square root of 14. If we wanted to multiply square root of 2 times 2 take away square root of 6, it would look like this. So we would get square root of 2 times 2. So this would be 2 square root of 2. And then square root of 2 times square root of 6, we're going to take away square root of 12. And now let's check square root of 12 and see if we can simplify that. 4 times 3, 2, 3. All right, we could pull out these, so 2 square root of 3. So we can say this simplifies to 2 square root of 2 minus 2 square root of 3. But because those radicals don't match, we can't combine it any further. All right, and then this one, just like if you were multiplying binomials, you can do the FOIL method because there's 2 and there's 2. So fronts, square root of 5 times square root of 15. Well, 15 times 5, that's going to be square root of 75. F. And then the outsides, square root of 5 times negative 3 square root of 2, that's going to be negative 3 square root of 10. Insides, minus 2 square root of 6 times 15, that's 60. 6 times 5 is 30, that's square root of 90. And then lasts, that's going to be a plus because it's negative times a negative, 6. And then 6 times 2 is 12. All right. So now let's simplify these and see if we can combine anybody. 75, that's going to be 25 times 3. And you might be able to see 25 is a perfect square, so that's 5 square root of 3. And if you didn't see that, you could do the prime factorization even further, and then you'd see that would be 5 times 3. And then for 10, that's 5 times 2, but we can't simplify that anymore. 90, that's going to be 3 times, oops, you know what? I can do 9 times 10. 9 is a perfect square. So the square root of 9 is 3. So this is going to end up being, I have to multiply it by what was out there, 6 square root of 10. And then for square root of 12, we have 4 times 3. 4 is a perfect square. So I have 12 square root of 3. All right, now anything that has the same thing in the index, we can combine. So these ones we can combine. So 12, we have 15 square root of 3 and negative 9 square root of 10. That was a lot of work there, but I don't think it's anything that's like more challenging than what you've been working on, so I think you'll be able to do that. All right, 36, rationalize in the denominator. All right, so we are not supposed to have a number like that in the denominator. So if we have something like that in the denominator, we want to get it out. So in a case like this, because 21 is divisible by 7, we could say it's the same as 21 over 7, which is 3. So that works. For this one, we can't combine 2 over 5 like that because it won't just like go away because it doesn't go in evenly. But what we can do is we can multiply the numerator and denominator by the square root of 5. We get square root of 10 over square root of 5 times square root of 5. That's going to be square root of 25 or just 5. So when you multiply that times itself, you're going to get whatever was inside there, and that makes it go away from the denominator. To do it once, but because this is a third root, we need to do it twice because we need 3 of them down there. So third root of 2. Now we have 3 of them down there, so we also have to do it in the numerator 3 times. I mean, like 2 more times, okay? So that's going to give us in the denominator, that's going to give us 2. And in the numerator, 2 times 2 is 4, times 9 is 36. So we have third root of 36. And again, the reason why we had to do that 2 times here is because we have the third root. In order to make that go away, we have to have this times itself 3 times. So we had to do it twice down there. So we have to also do it twice in the numerator. And now let's just do the prime factorization for 36 to see if that's something that we can simplify at all. So we have 18 times 2, 9, 2, 3, 2. All right, so there's nothing that we have 3 of there. So that's as far as we can simplify that. All right, so for this one, just to make sure we've got this, 4th root of 3. So that means we need 4th root of 3. We need this 4 times. All right, so now there's 1, 2, 3, and then that one that was there was 4. And in the numerator, we have to also do it 4 times. All right, so in the denominator, we are going to just have 3. And in the numerator, we're going to have the 4th root of 3 times 3 is 9, times 3 is 27, so we have to do 14 times 27, 378. All right, and we can see if, let's see, all right, they're not going to have us try to clean that up. We could do the prime factorization and see if we have 4 of anything, which I don't think we will. All right, so for this one, if we want to get rid of a situation like this, we need to do square root of 3 take away square root of 7. All right, and when we multiply those, and then we also have to do it in the numerator. And if we multiply those out, just FOIL it, and then clean it up, you can see that it gets rid of it in the denominator. And then once we have it like this, we can see like we have a 2 and a 4 here, so we can simplify those. So final answer would look like that. All right, and I think this is the last lesson in this. All right, so here, square root of 2 times square root of 2, that's just going to be 2. Let's see. All right, so here they're telling us this rule. This means there's a little 2 in there, even though there's nothing there. And this is the same as 2 to the 1/2 power. So if we have a fraction exponent, that means we're going to put it into a radical. Whatever's in the denominator is going to go there. So these 2 things are equal to each other. And if we think about it, these bases are the same and we're multiplying, so we have to add these. 1/2 plus 1/2 is 1, so that's the same as 2 to the 1, which is 2. Or we could say square root of 2 times square root of 2, which is 2. So if you have fraction exponents, that means that you have radicals, and that denominator goes in the index. So same with these ones, except because they're third roots, we're going to say they're 5 to the 1/3 power. 5 to the 1/3 times 5 to the 1/3. The third plus a third is 1, so it's the same as 5 to the 1st power, or 5. All right, these are all just giving different examples of that. Also, if we have 5 to the 3rd power like this, we could say that this is 5 to the 3rd power to the 1/2 power. And if you remember, when we're taking a power and raising it to a power, we multiply those. So 3 times 1/2 would be 5 to the 3/2 power. So 3 times 1/2, that's 3/2. So if you have something like this where you have an exponent and a radical, this is going to be the numerator, and this is the denominator, so 5 to the 3/2. So for this one, 2 to the 4th to the 1/5, well, we'd say that this is the same as 2 to the 4th, and we're doing the 5th root of it. So this is here, and this is here. Or we could say that's the same as 2 to the 4/5. All right, so for this one, if we wanted to rewrite this with the exponents, we would say 7 to the 1/2. Times 7 to the 1/3. And because the bases are the same, we can add 1/2 plus 1/3, which is not lovely because the denominators aren't the same. So we have 3/6 plus 2/6, which is 5/6. So we could say that's the same as 7 to the 5/6 power, or the 6th root of 7 to the 5th power. Okay, so for this one, let's see how it would help us here. This would be 4 to the 2/3 divided by 4 to the 1/5. Okay, so now because we have a 4 and a 4 here, we can just subtract the exponents. We could say 2/3 take away 1/5, well, times 5 times 3. This is 10/15 minus 3/15. That's 7/15. So we can say this is the same as 4 to the 7/15. Or we could say 4/15 root 7. All right, so just like we can do fractions here, we can also use decimals. 1/2 is the same as 0.5. So you can just do the same math, but with the decimals instead of the fractions. All right, and that's it for chapter 5. So if you're able to get through all of those, wonderful. And if not, no worries. Reach out if you need anything this week.